In the next section, we'll talk about entropy. It's a somewhat misunderstood notion. Poor entropy has too few friends. But you can't really talk about compression without talking about this notion of information content. And the context of Huffman codes makes it very concrete, I think. So let's dive a little bit into this. The formal definition of entropy is given here. What you have as the input is a probability distribution, a discrete probability distribution where you have n possible outcomes. Anything we should discuss in the plenum? If not, let's discuss entropy. So we have something random, a random variable that has n possible outcomes. Here, just the numbers 1 up to n. And they have different probabilities. And the meaning is the outcome to have value I is happening with probability pi. Then we can define this mysterious notion of entropy as this, often denoted by H. And it's this sum, or a bit. I think this is the better one to keep in mind because it has more intuitive meaning that I'll come to. For now, it's just a definition, okay? So what can we say about this? If we have n such probabilities, it's always at most log n, and it's at least 0 because this is, well, you can figure out, pi are all between 0 and 1. So because these are probabilities, right, then of course pi is in 0, 1, some real number. You achieve the maximal entropy if all the pi are equal. They're all 1 over n. That gives the maximal entropy. But okay, I don't want to bore you with a list of properties of this notion before we discuss why it's useful. The way why we study this in the compression chapter is that entropy is a measure of information in a distribution. So it's a bit awkward to talk about information in some random process. But think of it as this. You're hiding an interval somewhere on the unit interval. So you pick some little interval that lies somewhere. And my task is to ask yes/no questions, as in this game, 20 questions, to nail down what interval you've picked. Okay? So what could I do to find your interval? Initially, I don't know where it is. All I have is that it's somewhere in the unit interval. So my area of uncertainty, or the area of possibilities, is the entire unit interval. And then I'm going to ask you a question, namely, is your point that you pick from your interval, is that to the left or to the right of the 1/2 mark? And because you're picking something from this red thing in your case, but I don't know. But you say it's to the right. Okay. So with one question, I have cut my area of uncertainty in half. And of course, I'll just keep doing this. If I ask you again, the middle of this range, 3/4 mark, and you'll say, okay, it's left of that. So I'll reduce it to that part. Another time, you say it's to the right of 5/8, and so on. And then, okay, at this point, we'll stop the game and say, okay, you've found my range. All the numbers I've chosen are from this range. And I needed 4 questions for that. So the way to think about it is, if your interval has a specific length, that's what counts for the number of questions you need. The interval here was the interval between 11/16 up to 3/4, and the length is 1/16. Because that's a negative power of 2, you can nicely write it as log of 1/p is 4. Log of 1/16 is log of 16. That's 4. So all the logarithms here are base 2. It's a computer science class, right? Also here, these are all base 2. Maybe it's worth writing down again. Good. So in a way, this term that pops up here also is the term that pops up here. And you can work out that this doesn't work just in this example I gave you. It works for other intervals as well. So the way to intuitively think about entropy is it's how often do you have to cut your unit interval in half before you found this red interval? And the answer is log of 1 over pi times. Now, I've chosen nice numbers here so that it works out precisely and without any fudging. In general, because we can do this with randomization, you can still achieve it, but maybe not with such a simple strategy. But the notion to keep in mind is it's the expected number of these yes/no questions that you need to nail down a random value from that distribution. Okay, that's what entropy intuitively means. What does that have to do with information content? There's nothing random in a string, right? We're just starting with a text. We will come back to that. But first, let's look at the connection to Huffman codes. If I have an alphabet and probabilities, so I'm not looking at a fixed text for the moment. I'm looking at encoding one symbol at a time, and the symbols are chosen randomly, but with given probabilities. For example, you roll a dice each time you want to you want to have a next letter, and whatever comes up is your letter, uniform between 1 and 6. If I have that situation, I would like to send the letter I, the outcome I of my random choice, which happens with probability pi. I would like to send that using log 1 over pi bits, because that's what the entropy tells you you should need. You shouldn't use more than log of 1 over pi yes/no questions. Each yes/no question can be stored as 1 bit. So that's the number of bits you'd like to use. But of course, that can be problematic because this is a continuous function. It need not be an integer. Might be any number like 1.5. So if we want a code word of that length, good luck, that won't work. We can still do that in some average sense, but that's beyond beyond the section here. So if you start with an alphabet sigma and probabilities for the letters, and remember we defined Huffman codes for any weighted alphabet, but probabilities are fine weights. They just additionally happen to sum to 1. So I can apply Huffman's algorithm on this alphabet with the probabilities as weights. Then I get a code tryout, which has a certain expected code word length, L of E. And then I can prove that this lies between the entropy and entropy plus 1. So I have very precise sandwich bounds for how long the expected code word length in this case is for the Huffman code in terms of this entropy of the probabilities that we start with. To prove this, we have to prove the two inequalities, this one and this one. We'll do this one first. So whatever comes out, the expected code word length is at least the entropy. That's kind of alluding to what I said intuitively before. The entropy is this best possible number of questions. Then Huffman's code shouldn't beat that, shouldn't be able to get better than that. The formal proof would work like this. Whatever prefix-free code we have, so we don't even use that this is a Huffman code, we just use any prefix-free code. We can say that induces some weights on the alphabet by using the code word length. So we take the length of the code word for AI, but then we take 2 to the minus that length. So the longer the code word, the smaller the probability to see that letter. Okay? Which makes sense. Huffman gives shorter code words to more frequent characters. Now there's a thing called Kraft's inequality, which says if you have any prefix-free code and you take its code words and do this kind of weights, then these weights sum to at most 1. And the reason is very simple. So for Kraft's inequality, suppose you have any kind of code trie. What it says, if I take all those leaves and I assign them weights depending on their depth. So these are depth 2, so it's a quarter. This one as well. This one's one further down, so it's 1/8. And these are even one further down, 1/16. And the claim is, if I sum up these numbers, it's at most 1. Now you can check this in the example, fine, it will be exactly 1. But why is this true in general? Well, you can go level by level. You start at level 1. We have a weight 1 to distribute from the root downwards. And we say 1/2 goes here, 1/2 goes here. So at this level, I have 1/2 on each of the internal nodes, or leaves if I have some. And you keep repeating this process. Now in each step, you're going to at most double the number of nodes that are still alive. And some of them consume this. But you'll always have exactly this length left to assign to each leaf that you meet along the way. But you started with 1, so you never create weights from anywhere. You just pass them down. That's why the sum keeps at most 1. All right, you can look up the proper proof on Wikipedia if that was too quick. So we have some weights for these letters, and they're summing to at most 1. The second step is Gibbs inequality, which is really just this middle part. When you have one probability distribution, so some PIs that sum to 1, and some Qs that sum to at most 1, then this is the entropy, right? This is the same term that we had before, summing over all letters, PI log of 1/PI. Then if you take the same term, but you replace inside the log the P by the Q, you only make this whole thing bigger. That's Gibbs inequality. And the proof is fairly boring. It's just an analytic arithmetic proof of using the derivatives and so on. It's not insightful, so I'll skip it. And that's all we need. So we start with our entropy, write it as the sum, use Gibbs inequality, which relies on this inequality from Kraft's inequality. And that is exactly the expected code word length, because these QIs are negative powers of 2. So if you wanted to spell this out, 1/QI, well, this one is log of 1/2 to the minus E of AI length. 1/, and 2 to the minus cancels, right? So it's log of 2 to the length of E of AI. And now log and 2 to the power of cancels, right? So we're left with this, and that sum of PI times the length of the code word, that was the definition of the expected code word length. So it's basically all falling in place. That was that part. We still have to prove the upper bound. So we now know every prefix-free code has expected code word length at least the entropy. That's also true for Huffman because it's one prefix-free code. The other direction is only true for Huffman's code, but we'll show it in an indirect way again. So we now have to show that whatever Huffman's code looks like, its expected code word length is never more than entropy plus 1. What we'll do for that is we'll construct a totally different code, but it will be a prefix-free code. And then at the very end, we'll use that Huffman's code is an optimal prefix-free code, so it must be at least as good as that code that we constructed. How do we do this? We start again with setting our QIs, but this time we start with the probabilities. So you can interpret this as rounding the pi's to powers of 2, negative powers of 2. Right, we take 1 over pi and the log of that. That's rounded up. And then 2 to the minus of that. So that is roughly, again, pi, but it's rounded to the nearest, what is it? Smaller negative power of 2. Right, it's rounded to the, it's rounded up, but then it's a minus in front. Okay, now if we insert this into our computation, if we pretend we had code words of those lengths, that would be this L of E. If you simplify that, it turns out to come out at h plus 1. Why do we have the plus 1? Well, because we round up the log here, so that's at most log of 1 over pi plus 1. And then you can pull the 1 out of the sum, the pi sum to 1. That's where this plus 1 comes from. So what we have to show is that there is a prefix-free code, E prime, where the code word lengths are the QIs. Or at least they're upper bounded by this. That's enough. Okay, let's reorder the characters so that life is convenient, so that the ones with the smallest Q come first. That's just renaming. And then we'll construct this code by induction. If we have just 2 letters, then we'll assign a single bit. There's only one such code. We'll assign a single bit to the 2 characters. Because these are sorted, the Q1 at least is at most 1/2. And so, well, they're all at most 1/2 because they're of this form. I was struggling to see why in general, but because whatever probabilities you start with, they're all between 0 and 1, and so if you round down to the next negative power of 2, then 1/2 is the biggest you can have. So that's correct. And if you calculate that, that's 1 over at most 1/2. So this is at least log of 2, which is 1. And that is the length of the code words. So we've shown this part is true for 2 characters. Okay. The code word lengths are at most log of 1 over qi for both of those. That's the inductive basis. For the inductive step, we look at more letters, at least 3. Now, similar to Huffman, but slightly different next step, we take the 2 with smallest weight. These are these 2, right? They're sorted. A1 and A2 have smallest weight. I'll replace them by their boxed variant again and assign it not the sum of the weights, but something different, 2 times the larger weight. So that sounds strange, but that's what you have to do if you take the lengths of the code words. They both get the length of what comes down plus 1 bit each. All right. There's 2 cases. If the 2 Qs were the same anyways, then this is exactly what Huffman's algorithm would have done. Otherwise, Q1 is the unique smallest value. And that means we can also bump it up to Q2, and it still sums to at most 1. And the reason for that is, again, a little picture proof, if you allow me. All of the Qs are powers of 2. So we might have 1/2. Maybe then there's a few 1/8s. And maybe, okay, now I'm not drawing this nicely. It should be like this. So I have that one, and this, and this, and this. And then maybe the smallest is just 1 over 16. So if I start with from 0 to 1, the entire length, I might have used up 1/2, and then 1 over 8, 1 over 8, 1 over 8. These are my q's. And then 1 over 16. So the situation we're saying here is q1 is the smallest, and it's the unique smallest. There's no other equal value. Then no matter how I choose the others, if they sum to 1 before with this q, I can double q1, and it still fits in this strip. Because the only way how it can be smaller than the previous one is it's cut at least in half. So I can double it back and I have the space for it. If I had the space before, I have the space after. So what this means is we can use this double the larger value instead of taking the sum, and it's still a valid probability in the same sense. And of course, these 2 times q2 again has this shape of being a negative power of 2, which wouldn't have been true of the sum. Then we apply recursively the algorithm to the smaller alphabet, weighted alphabet. So we get some code words back that satisfy this by the inductive hypothesis. That's spelled out here. And so what does that mean here? The new q for this boxed letter is 2 times q2, and a factor 2 in the log just gets pulled out as a -1, a factor 1/2. What does that mean for our final code? So we construct the code words for A1 and A2 as the code word for the boxed letter plus an additional bit at the end for the 0-1 distinction. So they're just one longer, and that means they're both bounded by their respective q's. All right, that's the end of the induction. That means we've proven this. We found a code where each code word is bounded by this thing. And as we've calculated up here, the expected code word length of a Huffman code is better than any prefix-free code's expected code word length. So it's at most L of E prime, expected code word length of this code. And this code's expected code word length is upper bounded by this sum. So that's just sum over the pi log of 1 over pi, but we've shown the length of these, sorry. That's sum of pi length of the code words. And then we upper bound this using our result to that. And that was upper bounded as h plus 1. It's a bit of a lengthy calculation and proof, I understand. Apart from this little step in between that I waved my hands a bit about, we've been fairly formal. And it's a nice constructive proof as well, because it's not just a statement about this about these quantities, because it gives you a concrete code as well. Maybe constructing it on an example is helpful. Let's wrap up this part with a little bit of interactivity. We've had very little of that today. This is not specific to the last theorem. This is zooming out overall, so the entire thing. And you're asked to read carefully again. What I mean by a fixed length character encoding is just something like ASCII. You're given the same number of bits for every symbol. All right, we eventually had 130 people on the attendance code, so there's a bit of a gap still. Certainly none of them will have just logged the attendance code and then switched off. I think we have a record number of people streaming or using the live stream today. So the room's not so bad, guys. It's quite cozy and nice, but yeah, I get the rain was not fun. Pardon? I know. I don't get to choose the rooms. To be frank, I mean, I didn't get much to say, much of a say in this. I'm not fond of the South Campus one. But we'll be there tomorrow, right? So yeah, exactly. Yeah, that will stay. Okay, so 100 people voted. We can continue moaning about the rain and the rooms later. Let me show you your results. I allowed several answers. So it's a bit of a trick one. So the third one, I'll comment on it. Again, like you keep doing this. You keep changing your answers. You're only cheating yourself. So first of all, it's all on record, so I can go back and see what the distribution was. It's just not so convenient, right? And secondly, you'll not be marked for the right answer just for playing along. But yeah, if it makes you happy. All right. So I put always because in a way a fixed length character encoding is a prefix-free code, right? If everything's of the same length, nothing is a prefix of something else. And so any such fixed length encoding is one prefix-free code, and Huffman always gives you something that's at least as good. Right. So if you interpret more efficient as less or equal, then you could say always, because it's an optimal prefix-free code. If you're more strict and you interpret more efficient as strictly more efficient, has to be strictly better than this, not just equally good. Then the right condition would be, well, a sufficient condition is this. Sometimes this condition is enough, but maybe not always. For example, a stupid example would be just 2 letters. There's only one code signing 0 and 1, but the entropy could be slightly less than 1, but it won't be less than 0, right? And you get similar situations if sigma is close to or is a power of 2 and the entropy is just below that. It might be that the Huffman code is the same as using fixed length character encodings. Whereas if this condition is satisfied, if your entropy is log sigma minus 1, then Huffman definitely gives you a strictly better result. All right. Hey guys. I just want to make sure you don't miss the second part. So even in case you've seen this before, this is something that's not always discussed. I want to come back to a single text. So we're in the compression chapter, and I talked at length about entropy as this probability of this property of a probability distribution, but there's nothing random in a string. We're just given one string. But there's a notion that ties these two things together and makes it round again. We can take a fixed string and define something like probabilities by taking the relative frequencies. So you count how often each letter occurs and divide by the length of the string. If we do that for some text, and use our Huffman-coded length of the coded text. What do we get? Well, we can reorder, as I said before. We sum up all the characters. How often does each character occur? How long is the code word for that character? And I can rewrite that as n times this sum. And that sum is close to the entropy, but it has this term. So, I mean, I've just smuggled out this factor n here. And then I have a pi here, the probabilities I've defined, even though there's nothing random. So I can say the compressed text size is n times this expected code word length. Okay, that's essentially just by definition. But then using the theorem that we spent some time proving, we can say that this length of the coded text is bounded between an entropy and an entropy plus 1 times n, where the entropy is the entropy of these probabilities. Okay, it was a bit long-winded, but this notion is called the empirical entropy of a string. And that term I want you to remember, because that's a useful notion. If you're given just a string, coming back to Kolmogorov complexity, we've already said, okay, how much can you compress a given string? It's a somewhat unknowable task because you can't compute it. Kolmogorov complexity, the ultimate compression would be the shortest program producing that string, but we can't compute that. So what other measures of this string can we define so that we can compress it, but things that are a bit simpler, a bit more easy to handle than this Kolmogorov complexity? And one option is to look at the empirical entropy, which is a measure of how much are the characters random and how much are they predictable. And that gives you a very precise quantitative notion for this intuition. But all that it is you take the relative frequencies of the characters and then the entropy thereof. All right, let's wrap up the discussion of Huffman. We've never analyzed the running time of the algorithm, and it's an algorithms class, so can't leave you in that state of sin. So how much does it take to construct a Huffman code? We can use the priority queue as I mentioned earlier. So we built the priority queue by starting with all the letters and their initial weights. And then for each letter, we have 2 delete mins and 1 insert. If you remember back from Unit 2, we can do both of these operations in log sigma time, log size of the priority queue, which is at most sigma here. So that gives us this order log sigma overall time. It's fairly fast, even if the alphabet is somewhat big. We can actually do it faster if the characters come already in sorted order, sorted by weight. There's a lovely algorithm using 2 queues instead of a priority queue. So 2 standard queues, first in, first out. The overall time to encode a text with the Huffman code, once that code is already done, that's linear in the size of the input and output. So I have to read each letter in the input, and I have to produce the coded text. So I have to write each bit in the output. But that's pretty much it. That's achievable in that time. Okay. On the practical applications of this, Huffman is a building block of most compression methods that are used, just because it's super fast, has these nice guarantees. In isolation, it's maybe a little limited, but it's a useful building block. There's a few things that become relevant there if you want to squeeze the last number of bits. I mentioned how you can use canonical Huffman codes to deal with these type-breaking rules and so on. But we'll leave it with that. It has nice theoretical guarantees. And remember, this is a class about the eternal truths of algorithms, so I like that. It's also very fast for the decoding part, at least. A slight disadvantage is that it needs 2 passes over the input, the way I described it. And there's no easy way around this. There's a more complicated variant of Huffman codes Now, I just want to mention that you don't think it's impossible, but we won't cover it, where you can read through the text and you always keep the number of character occurrences up to this point is what you built the Huffman code on. But there's a smart way to do that without recomputing the Huffman code each time. Then you can do it in one pass, but it's not used that much because it's overall slower. The more serious disadvantage is that we have to store the code alongside the text. And so there's a certain minimal size of the text before this becomes useful. That's one of the things that we'll work around in the next parts.